Okay, today we are going to define some of our thermochem vocabulary, and then we're going to do some practice problems calculating specific heat and enthalpy change using a calorimeter. This is all stuff we've actually done before. Some of the terminology may be new, but we have calculated these things in honors. Think about that red hot penny lab. It's pretty much a variety of the same. We will get into delta E and how to calculate those things in the next play posit. The quest that goes with this is 19A. That's thermodynamics. Okay, so thermochemistry. Thermochem, it's the study of energy changes that accompany chemical reactions. That we know. When we're talking about energy, we're talking about the capacity to do work or to transfer heat. And there are a couple of different units we use for energy. Just some review. We have the calorie. We talked about calories briefly last year. It's the heat needed to raise the temp of 1 gram of water to 1 degree. There is a difference between the calorie with a lowercase c and an uppercase c. And uppercase c is the calorie you see on food labels when we're talking about food calories. And that is actually the same as 1,000 calories or a kilocalorie. And then we have the joule, which we are plenty familiar with. The joule is equal to 4.184 joules is equal to 1 calorie. That is our main SI unit. When we're talking system and surroundings, system is what we're looking at, and surroundings everything else. That's pretty straightforward. Work. So work is the product of force times distance. We talked about that a bit in the last unit. It's the product of force and distance through which the force works. So we're going to look at force both done on a system and work done by a system. And then we have heat. Heat is just thermal energy. Remember, there is a difference between heat and temperature. Temperature is a measure of the average kinetic energy, aka thermal energy. In this case, heat is just the thermal energy itself. It can be transferred and it flows from hot to cold. That part should all be review. Some of the new things we see. Zeroth Law of thermodynamics. I can't remember if we talked about this last year or not. We can talk about the name and why it's called the Zeroth Law later on. I don't want to waste time doing that here. But essentially all it is if you have two objects in contact with each other and they reach equilibrium, and then you take one of those objects, say object 2, and put it in contact with a third object, and then they reach equilibrium. Essentially, what this means is that all of them are at equilibrium. So it's basically a simpler term for a transitive property, right? The energy is conserved, etc., etc. Speaking of energy being conserved, first law of thermodynamics is our law of conservation, right? Energy cannot be created or destroyed. And the sum total of energy in the universe is constant. Constant, yeah. So thermodynamics. If we actually break down the roots here, thermo and dynamics, we get heat. The literal translation is heat power, which is cool. So that's why we're looking at both the heat and the work when we're talking about the total energy, because they are related to each other that way. Internal energy, we've talked about internal energy a little bit in various forms, but you may not have heard it in this context. Internal energy is just the sum of potential energy and kinetic energy in a system. So if we're looking at a graph, I'll show you in a little bit, we'll look at the potential energy graph and we can show you what that means. Now, we will calculate the internal energy, delta E. We'll use the equation delta E is equal to Q, which is our heat, plus our work, which is W. And that's really the second the second quest gets into those equations and those types of problems, and we'll do that in the second play posit, but I wanted to give you the equation now. If you remember back to like the whole endothermic and exothermic reaction process, remember that if your enthalpy is negative, it's an exothermic reaction, heat is being released, and if your enthalpy is positive, heat is being absorbed. Same thing with Q. Remember, Q and enthalpy, or delta H, are very similar to each other. So this means that heat is absorbed, and heat released. All right. Now, work is the trickier one. You can also have positive and negative signs for work. For work, it is positive when work is done on a system. So, other words, if we are talking about like gases, if we compress a gas, right, that is an example of when we would be doing work on a system. We are compressing a gas, we are forcefully causing its volume to get smaller, and we are therefore increasing the pressure. That would be a positive work value. Negative work is when work is done by the system. And that would be something like expansion. So we increase the temperature, and then the only way the pressure would increase, and then obviously if the pressure is increasing, we need to relieve that pressure. So for it to relieve itself, then the volume would also increase, and then we would get our expansion. Okay, I'm going to erase that part of the example though, because I want to be able to put this definition here for a state function. State function is definitely a newer term. This is just a property that is independent of past and future behavior. So, for instance, we can go from A to B, but we don't really care about how we get there, right? You leave school, or you leave your house in the morning and come to school. You leave school at the end of the day, go back to your house. Your bus route may not always be the same, or the way you drive in your car may not always be the same, but you still have the same beginning and end. Enthalpy. So the official definition is it's the flow of energy at constant pressure when there are two systems in contact. Now, we've talked about it, it is delta H, and something I want to remind you of is delta H is equal to Q when we have constant pressure. So that's why we're able to relate the whole endo-exo, positive delta H and negative delta H to here, because they are at the same, at constant pressure. Delta H is essentially just the difference between potential energy of your products and reactants. When we're looking at a graph, we can certainly see that difference, and we'll get back to that graph in a minute. That's with our activation energy and our delta H. The 4 ways we can calculate delta H that we're going to talk about in this unit. This is the one we're focusing on in this play posit. Q equals MC delta T, your MCAT. I know that's not an A, but it looks like an A. A lot of people just say Q MCAT. We'll get into Hess law with the next play posit. Then we have enthalpy of formations, which is delta HF, and bond enthalpies. A lot of this stuff we've done already. It's just going to get a little bit trickier with the wording, but we can do it. We will be fine. Your activation energy. If you remember this graph, if we're looking at the potential energy, your activation energy is the amount of energy you need to get your reaction started. So this is your activation energy, right? Activation energy. Delta H, all delta H is the difference between your reactants and products. So delta H is in this section here. Okay. Okay, so we're going to go over our first example of calorimetry. This is actually a problem we did in honors. You need that equation. Q equals MC delta T. M is your mass, C is your specific heat capacity. That's this thing here. And delta T is your change in temperature. Remember, that is T final minus T initial. That's a minus sign there. Okay, so in a coffee cup calorimeter, we have 100 milliliters of 1 molar sodium hydroxide and 100 milliliters of 1 molar hydrochloric acid, and they're mixed together. Both solutions were originally 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius, assuming that all solutions have a density of 1 gram per cubic centimeter and a specific heat capacity of 4.184 joules per gram degree Celsius. Calculate the enthalpy change for this neutralization. Okay, so I got some important values to identify. I got my T initial for both solutions is 24.6 degrees Celsius, and this is for both our HCl and for our NaOH. They would have the same starting point, right? Okay. And we also have our T final is 31.3 degrees Celsius. Okay. And then we've got this lovely density. This is going to be our lifesaver here. Although it might look a little weird. We've got this grams per centimeter cubed. What do we do with that? Well, it's easy. If you don't know by now, drill this into your head. Grams per centimeter cubed is the exact same thing as grams per ml. Oh my God, this problem just got a whole lot easier. I know. It's really not that bad. All right, so now, when you are trying to figure out how many grams, your M for this, we need the total mass. How many milliliters do we have? Well, we got 100 and 100. So that gives us 200 milliliters total times 1 gram per ml. We got 200 grams in our solution. Sweet. And I'm sorry, I should have made this an appropriate sig figs. This is really 1.0 gram per mole. We will take this number into account for our sig figs at the end of this problem, so keep an eye out for that. All right, we've got our Q. Let's plug in. We've got 200 grams. 200 grams and 4.184 joules per gram Celsius. And then we've got 31.3 degrees, our final temp, minus 24.6 degrees Celsius. Okay. Let's plug that into our calculator. All right, so we've got 200 times 4.184 times, I'm going to do parentheses, 31.3 minus 24.6, close parentheses, boom. I get 5606.56. So we get 5606.56. Let's check our units. Grams cancels, Celsius is gone, and we are left in joules. So this is 5606 joules, but we got to pay attention to the sig figs. We said 5,600 joules, 2 sig figs, right? Now, 2 things we have to consider. 1, we typically report delta H in kilojoules, and this is Q. We know Q and delta H are equal at constant pressure, so it's good habit to put this in kilojoules. So we've got kilojoules here. Now, we have to think about what is happening here. Did the temperature overall go up or did it go down? Well, temperature goes up here. Therefore, we know the solution got warmer. Therefore, energy is being given off. So this isn't a positive 5.6 kilojoules. It's a negative 5.6 kilojoules because it is exothermic. It is being given off. Okay. Next one. We've got calculating heat capacity. So, same equation, but this time it says copper is placed in a calorimeter of water. Think about your red hot penny lab. This is your red hot penny calculation, essentially. So, the key here, we know that the negative Q of our water is equal to the Q of our copper, our Cu. So let's go ahead and figure those things out. We've got Q of copper, and we know that it's 46.2 grams. We don't know our specific heat, that's what we're calculating, but we do know that our final temperature is 21.8 degrees Celsius minus 95.4 degrees Celsius. And then we should also set up our water. So water is equal to 75 grams, 4.184 joules a gram Celsius. And then we've got 21.8 degrees minus 19.6 was our original. Okay. Sweet. So if we go through and multiply everything here, 75 times 4.184 times 21.8 minus 19.6. I'm doing this on my own calculator just to save time. We get 690.36. Remember your units, that's joules. Now we know that the negative Q of water is equal to the Q of copper. So now we've got negative 690.36 joules, and we'll account for sig figs at the end. This is equal to 46.2 grams, and our CP, our specific heat, and then 21.8 minus 98, or 95.4, is a negative 73.6 degrees Celsius. Okay, so I've just combined my terms here. All right, so to solve for CP, we have to rearrange. We should divide both sides by 46.2 times my negative 73.6 degrees Celsius. The negative. We divide here, same thing. Negative 73.6 degrees Celsius. Those negatives should cancel out, and with 3 sig figs, I get a specific heat of 2.03 joules per gram degree Celsius. Let's check the math in the calculator. We've got negative 693.36 divided by 46.2 times negative 73.6. We do get 0.203. Cool. Alrighty. So this one is a little tricky. It's along the same lines of your first problem. Constant pressure calorimetry. So it says when 1 liter of 1 molar barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of 1 molar sodium sulfate solution at 25 degrees, the white solid that forms, barium sulfate, and the temperature of the mixture increases. So we know this is going to be an exothermic reaction because the temperature is increasing. Now when we consider this reaction, we need to consider the ions involved. Barium 2+, and that is supposed to be sulfate. Let's try that again. Sulfate 2-, and that is a 1-to-1 ratio. You do get your barium sulfate. So when they ask about your enthalpy change per mole, in this problem you're lucky, you don't have to do anything extra, but you may have to check because the moles might affect you based on the balance equation. Okay. So when we're looking at our density, we got to figure out first our total mass, right? We're still using Q equals mc delta T. mc delta T. And we know that that our Q water is equal to the negative of our Q barium sulfate that we're forming our solid, right? So it's just the negative can go either place. You can do negative Q water equals Q barium sulfate or vice versa, as long as you know that they're opposites, right? Because energy is being transferred. That's the important part. So we've got, how many liters do we have total? We've got 2.0 liters. So therefore, we've got 1,000 milliliters that we have to multiply by for every 1 liter. And then we've got 1 ml for every 1 gram, because that is our conversion factor. We end up getting 2,000 grams for this bad boy. All right. 2,000 grams. So 2,000 grams. You can use the same specific heat, 4.184 joules per gram degree Celsius. And then our temperature change. So 28.1 degrees Celsius was the final, minus 25 degrees Celsius is the initial. And we can get our, remember this is the water, this is the mass of our water here, right? So if we figure this out, we've got (2,000) times 4.184 times, what was it, 28.1 minus 25, which should be 3.1. I don't know why I put that in the calculator. And when we do, we get this nice big number, 25940.8. All right. So this is equal to 25940.8 joules. But remember, this is the amount of joules for the water. So for barium sulfate, we need to put that negative sign there. So negative 25940.8 joules. And then we also need to make sure that we have the right number of sig figs. We've got 3 sig figs pretty much everywhere. 3, 3, 3. And then we can go for, oh, I'm sorry. We have 2 sig figs. I lied. We can go with 2 sig figs. So this is negative 26,000 joules. And then remember, it's delta H. It is your Q. So we should say that Q is in kilojoules for this. So we get negative 26 kilojoules as our answer. Sweet. And that makes sense because the temperature went up and the amount of energy we were giving off corresponds to that. Okay. Have a great day.